Welcome to Death to the IOC, What's Next in Threat Intelligence in South Seas ABE, with Bhavna Soman, who is a security researcher at Microsoft. Before we begin, a few brief notes. Stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2 during the day and for the welcome reception at 5:30 p.m. this evening. The Black Hat Arsenal is in the business hall on level 2. A quick reminder that lunch will be in Bayside AB from 1 o'clock to 2:30. And don't forget the merchandise store on level 2 and session recordings from Source of Knowledge. They have a desk on every level. Also, thank you for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while we wait for your voicemail to pick it up. All right, without any further ado, our speaker, Bhavna.
Sweet. Thanks for the intro, Grant. Good morning, everyone. Thank you so much for being here. I know that this is a 9 a.m. slot, super, super early. Hope everyone got their caffeine in. We're going to be talking about death to the IOC, what's next in threat intelligence. Here's a little bit about me. My name is Bhavna. I work for Microsoft Defender Research. In the past, I used to work in threat intelligence and APT response. And now I write models that classify malware in real time. So I work in machine learning. And this project is kind of this amalgamation of these two disciplines that I've worked in, kind of straddles data science and threat intelligence. So when I was a threat analyst, one of the things that struck with me was how manual that job is. A lot of people think of automated IOC feeds when they first think of threat intelligence, but the job of a TI analyst is actually a lot more than that. There's some forensics, some reverse engineering, and there's actually a lot of reading. To understand the type of the threat actors that their organizations care about, TI analysts go through a lot of literature, whether it is something that they got from their information sharing organization, their ISAC, their CERT, or just publicly available threat intelligence blogs. They go through all of these documents to understand what are the vulnerabilities these actors are targeting, or what are the legitimate binaries that they're abusing. And all of this data exists in unstructured text right now, which requires manual processing. Let me give you an example of the type of workflow that a TI analyst has. So for example, you're an analyst whose organization is worried about attacks from an Eastern European country. So you go out and start reading about attacks that have originated in that region. So maybe you find these 3 actors, APT 28, 29, and Dragonfly, and you start reading about them. You see that 28 and 29 have been active longer, since about 2007 or 8, and then Dragonfly is more recent, about 2011. You see that Dragonfly has more cyber espionage targets, whereas 28 and 29 are more politically motivated organizations. And then maybe 28 has started using IoT attacks recently, whatever. So you get all of this information, and then you try and organize this. Maybe you start with like a shoebox of these TTPs that you gathered, the legitimate tools that they attack, the malware families they use, etc. But then you need to organize it even more so that you can extract the insights that will help your organization make better decisions. So maybe you represent it in a graph like this. Now you can clearly see the overlap between the TTPs that are used by these 3 threat actors that you care about. In fact, you can clearly see that there isn't very much overlap between them. In fact, APT 28 has a very complicated networking infrastructure that's mostly absent from the other 2. So maybe then you try and layer even more context on this graph, and maybe you overlay this with the prevalence of each TTP on its own. So now this is what it looks like. Now the size of the bubble is proportional to the prevalence of that particular TTP in the ecosystem overall, not just with these 3 APTs. So now with this type of visual, you can help your organization make some data-backed decisions. For example, you might say that, hey, let's prioritize our defensive choke points on credential dumping or pass the hash attacks. techniques which will help disrupt the actual toolchain of the attackers that we care about, as well as a large percentage of the attacks out there in general. And you might recommend that, hey, let's deprioritize things like time stomping and bootkits because they're really fancy, but they won't have as much impact for the security of our organization. So this is the type of insights that threat intelligence analysts are on the hook for generating, and right now they do this manually. In fact, there was a really good talk yesterday on the MITRE attack framework, and shout out to Katie Nichols and her team at MITRE who do this awesome, awesome work. But they shared some examples of their partners who are doing this type of analysis, and right now all of this is done manually. So can we do this with machine learning? That's the question that we were exploring. The architecture of a system like this would look roughly like this. We would have our input, which is the unstructured data, the written material that the TA analyst has access to. And then all of it would flow into this black box, which would then extract the actor names, the entities, and be able to build relationships between them. And then the output would be the kind of insights that I just shared with you, attacker graphs or timelines. So this black box, that's what we're going to focus on for this talk. This is my agenda for the rest of the talk. I will introduce the idea of named entity extraction. I'll talk about the recipe for building a machine learning / deep learning based cyber entity extractor. I'll share the training data you can use, featurization methods, models, and I'll share with you the assessments that we got from our data. I'll give you a short demo of a tool we've created, and I'll close with an example of how this can help drive impact in organizations. Okay, so what is named entity extraction? This is a wiki article about my favorite Game of Thrones character. If I pop the text from this article into any commercial off-the-shelf text analytics toolkit, like the ones available by Azure or Google, I can easily extract the entities that are present in this. So the entities would look something like this. Sansa Stark is a person. Eddard Stark, Catelyn, also persons, and Winterfell. Well, the toolkits that I looked at, they kept classifying Winterfell as an organization, whereas we know it's a geopolitical entity. But when I try to use those toolkits on an APT report like this, they fail. The types of entities that I would expect them to be able to extract look something like this. So I would want them to be able to say that, okay, dropping elephant, China strats, and patchwork are the names of the actor, whereas spearfishing and watering hole are the attacks or the TTPs that they're using. So this is the type of entity extraction that we want our algorithm to do. Okay, so here we start with the recipe of training our own entity extractor, starting with the training data first. For this experiment, we kept ourselves to a publicly available corpus. So we used APT Notes, which is a GitHub repository containing APT white papers going back to 2004. We also used a collection of threat intelligence blogs that were collected by our TI team between June 2018 and Jan 2019. In all, this data set had about 2,700 documents, and these graphs kind of show you a distribution some data analytics features about these documents. So the top chart shows you that each document had, on average, 2,000 tokens. The median was more like 1,400, and there were some on the tail end that had upwards of 70 to 80,000 tokens. The lower graph shows you the distribution of the tokens that we care about in this data set. So the tokens that we care about are the tokens that indicate the name of a malware family or the name of an actor or the phrase that indicates a MITRE attack technique. On average, only 1% of the tokens in our data set belonged to one of these classes. So this tells us two things. One is that we have a really small data set, and we know from past experience and literature on deep learning that deep learning methods sometimes don't work as well on really small data sets. So we'll be sure to try some statistical modeling methods in addition to the deep learning ones. And the other thing is that we have a class imbalance problem. So we'll have to take that into account in the models we choose as well as the assessments which we do. To get our labels, we used the Caret dataset, also provided by MITRE. Here I've included a screenshot of what is contained in the Caret dataset. It's basically, you can think of it as a list of all the APT attackers and the TTPs that they use. We used this as a list of tags, and we annotated our data from this list using longest extent pattern matching. So obviously, this labeled data set is noisy in a few ways. Longest extent pattern matching is not perfect. And also, the caret data set itself is incomplete. So there are some actor names, for instance, which are not present in the data set, so they got labeled incorrectly in our corpus. But short of manual annotation, that was the best we could do, so that is the method that we went with. I want to show you how the data gets labeled in this problem. So we use what is called the IOB style, which is very common in natural language processing tasks. IOB stands for inside, outside, beginning. And here you can see an example of how that annotation looks like. So if I have a phrase, Eddard Stark, which in all indicates a person, the first token in that phrase will be tagged with a B-person for beginning of person, and then all the subsequent tokens in that phrase will be tagged with an I-person, so inside person. Here's an example of what that would look like on a corpus on a sentence from our corpus. So this is a sentence about numbered panda. And if we tag it in the IOB style, this is what it would look like. So numbered panda is the phrase that indicates the bad actor, and the first token in that phrase will be a B-bad actor, and all subsequent tokens will be I-bad actor. Coming to feature extraction. So we used broadly two types of features that we experimented with. We used the traditional features that are common to natural language processing tasks like lemma, part of speech, word structure, etc. But then we used word embeddings. This is a type of unsupervised feature that we can extract in an unsupervised way. In a simple way, word embeddings are a way to encode the semantic context and the meaning in which a word appears in a numeric vector. So for example, if two words appear in the same context a lot or have the same meaning, we would expect their numeric vectors to have a high cosine similarity. This is just an example, a screenshot of generic word embeddings that I added to give you more context on what word embeddings look like on just a general data set. So here we can see that words that occur a lot in the similar context, like in the context of a kitchen, they are clustered together. And we trained our word embeddings on the TI corpus. So what we are expecting here is that the meaning of the words in which they appear in that cyber threat intelligence context will be encoded in their numeric vectors. So let's look at a few examples that show if this is happening. This is a visualization of our word embeddings generated on the cyber corpus, visualized using TensorBoard. Here we are plotting the 4 closest points to APT28, and we can see that out of those, 2 are aliases, so FACI and TG4127, and then 2 others are related to it by attribution. So we can see that the context in which these word appears, it's kind of encoded in this numeric vector, which is formed or extracted from the word embedding. Here's another example. If we look at the 3 of the 4 closest points to the word dog call, we see that they're Purim, shutter speed, and are you happy? And all of these are malware families that are used by one particular APT, APT37. This is an overall visualization of the tokens that are contained in the 3 classes that we care about, and we can see that the tokens that are in the malware and the actor class are clustered separately from the tokens that appear in the technique class. So basically, these 3 visualizations help us get some idea that the word embeddings are taking our model in the right direction. Let me share with you the architecture that we used. So it was quite simple. We had the text, the unstructured data sources, the blogs, white papers, etc., and we put them through just HTML and PDF parsers to get at the raw text. We put them through some lightweight text pre-processing, just white space normalization and removal of unprintable characters, and then we extracted the word embeddings. And in this experiment, we used the word-to-vec model, but there are others like GLOVE or FastText that can also be used. We then split the dataset into training and test 80-20. We extracted the custom features, joined those with the word embeddings, and then we trained our model and then tested our model respectively. So this was the first model that we experimented with that I want to talk about. Conditional random fields, or CRFs, can be thought of, they're not a deep learning method, it is a statistical modeling method, and it can simply be thought of as logistic regression, but for a sequence labeling problem. In fact, they're very commonly used for sequence labeling tasks, particularly in other natural language processing tasks, biological sequencing, and even in computer vision sometimes. We can say that CRFs have a short-term memory, and let me explain what I mean by that. Here you can see the matrix. That matrix is a matrix of transition weights between the various classes that we had in our data set. So for example, you can see that the transition weight from an O class to a B bad actor class is 0.22, which is positive. But if you look at the weight for a transition between an O class to an I bad actor class, it is -5. It's a very negative number, which shows that the transition between an O class directly to an I bad actor class is very unlikely, which makes sense, because in a sentence, you're more likely to get an O term and then a B bad actor term, and only after that will you have the I bad actor term. So this type of, this is the short-term memory that is encoded and learned by the model. Also, we did 2 experiments with the CRF because we wanted to make sure that the word embeddings that we're using are actually contributing positively to the model. So we did 1 experiment with the word embeddings and then 1 without. We also experimented with LSDM. LSDM is a deep learning method. It is a special form of RNN. We used 2 stacked bidirectional LSDM layers with dropout. We used categorical cross-entropy for our loss function and softmax activation for our final layer. This type of architecture is quite typical for the problem that we're trying to solve based on the literature. So what we're doing here is domain-specific named entity extraction, and this type of architecture is quite typical. The only tweaks we made was adding the dropout layer, and that's because I'd mentioned earlier that we're worried about the class imbalance causing overfitting, so which is why the dropout is meant to help the generalization. And we trained this using Keras and TensorFlow. Okay, we come to the assessments. So first I want to share with you the overall recall counts of the terms in our data set. Right off the bat, you can see that we had very few technique tokens, and that is a limitation of the data that we're working with here. The yellow bars indicate the LSTM model, the blue is the CRF without embeddings, the red is the CRF with embeddings, and the green is the actual counts of the tokens present in our data set. So we observed that for the actor class, the LSTM outperformed both the CRFs by a huge margin, whereas for the other 2 classes, their performance is kind of similar. Let's look at the precision and recall. So here we have plotted the positive precision and positive recall of our models. And you can see again that in terms of the precision, the 3 models have comparable performance where, you know, the trade-off might just be, hey, LSTM takes 3 times longer to train, so I'm just going to use a CRF. But with the positive recall, we see that the LSTM is still outperforming the CRFs. But there is one particular use case or scenario where we want to test this model, and that is its performance on unseen tokens. So in our actual use case, when we get a new document that talks about a new actor or a new malware family that the model has not seen before, we want it to be able to correctly label that as a bad actor or a malware family, etc. So that is why we want to measure the performance of these models on unseen tokens. And when we do that, we see a dramatically different picture. We can see that on the unseen tokens, the LSTM as well as the CRF, they severely dropped in performance. They have barely any recall, and even their precision has dropped. Whereas the CRF with embeddings, it has perfect precision, and it is the only one that has any type of recall. So that's the model that I'm going to be using in the demo today. All right, we're at our demo. So this is just a toy web application. Here you can paste the text, run the model on it, and then the model will extract the entities that we talked about, the actor, malware family, etc., and show and highlight those, basically. So let's try a dummy sentence on it. This is a blurb about PawnStorm, which is also an alias for APT28. We run the model on it, and we can see the output. So here the malicious actor is highlighted in red, whereas the techniques are highlighted in orange. And we can see that the model correctly identified pawn storm as the actor and credential phishing and spear phishing as the techniques. Let me give you some more examples. So I'll add another blurb of text. There are 2 paragraphs. They're unrelated to each other, but I just wanted to illustrate the breadth of actors and techniques and entities that the model can find. The first paragraph is about Scarlet Mimic. And when we run the model on it, we can see that the model correctly extracted Scarlet Mimic as the actor and spear phishing and watering hole as the attacks. The second paragraph is about a different malware family, Havextrat. It's the wiki blurb about it. The malware family is highlighted in purple, and it also identified in the second blurb some other actors that were present, Black Energy and Dragonfly. So this seems to be working quite well. But I want to give one more example. The reason for that is that I want to clearly illustrate that the model is not doing pattern matching or text recognition, but is actually able to identify the techniques or the entities based on the context in which they appear. Because that's the critical thing about the model. It should not be just being like a fancy regex. So if I type a dummy sentence here, like, okay, so if I type a dummy sentence like, this is a fancy bear, and fancy bear is the name of a known attacker, and if I run the model on it, the model should not extract any actor on it. And that is as it should be, because in this context, this is not the context of an attack. This is a fancy bear. I might be talking about a fancy teddy bear for all we know. And here we can see that the model did not call this out as an attacker, and that is how it should be. But if I type another sentence with the same phrase, but having the attack context, then I would like it to identify the actor correctly. So another sentence is, the White House was attacked by a fancy bear, and when we run the model on it, awesome. So we can see that now the model can correctly identify that as an attacker, and that's the critical piece. We're able to show that it's not just doing pattern matching and text recognition, but is identifying the phrases based on the context in which they appear. Awesome. So this is version 1 for us. This is an ongoing piece of research. The next things we want to work on, we want to experiment with attention networks, which have been shown to show good results for this type of problem. I also mentioned that we have a small data set, so we want to experiment with generative methods for data augmentation. Also, we want to experiment more with extracting more sophisticated relationships and also temporal relationships. I want to close with an example of how this can be used to drive impact. So I showed you this graph in the beginning where our imaginary threat analyst used this data to help their organization decide where they wanted to place their defensive choke points. We created a similar plot from the data set that we had, and here we plotted the overlap on the TTPs of a commodity malware family, Emotet, and then a collection of APTs. There are some snakes and pandas in there. But here you can clearly see the overlap between commodity malware family and nation-state attackers. Techniques like spear phishing, obfuscated PowerShell, process hollowing. We might think that they are advanced, but they're being used by commodity malware today. And this is further evidence of the blurring line between commodity malware and nation-state attackers. So now this sort of a visualization can be used by TI analysts to convincingly drive their organizations towards placing their checkpoints in these places, which will help them avoid not only the annoying commodity malware, but also the high-profile APT attacks. And we're helping them do this in an automated way without manual work. In conclusion, I hope I have showed you that it's time for TI to move beyond IOC feeds. I shared with you a recipe of how we can use machine learning to extract insights from the rich, unstructured data that we have. And then I give you an example of how this can be used to drive insight for the security of an organization. I would like to thank my teammates at Defender who have been amazingly supportive for this project. And with that, I'm open for questions. Yeah, there are mics over there. Yeah, go ahead.
Yeah, so I saw that your in-sample, I think it was like in-sample performance, like tokens that had been
I'm
seen.
sorry, I can't hear you clearly.
Oh, the performance for the samples that had been seen was rather high, and then the samples, the performance for tokens which hadn't been seen, which I guess is like out of sample in a way, was 1, which is, as I'm sure you're aware, is pretty uncommon for, like, it seems like the out of sample performance was like better than the in-sample. Am I interpreting that right? And like, how did that surprise you?
I'm sorry, I'm not able to understand the question clearly.
So there was a portion where you showed the performance with like recall, I think it was, on like
Unseen tokens?
Unseen tokens,
Yeah.
and it was higher than tokens that had been seen, and I just thought that was kind of unusual, and wanted to know what you thought about that.
Right. So yes, the precision of the CRF was higher on the unseen tokens, on just the unseen tokens, than the overall data set. And that's, I think my assumption underlying is that the unseen tokens were more likely to be in one of our classes. They were not just like words that occur in text in general. So that is why the model latched onto that and was able to perform higher on that. But yeah, that's understandable. Thanks.
Thank you.
Go ahead.
Thank you. We are out of time. We'll take those questions in the wrap room. Thank you, everybody.
Thanks.